Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wondered if you are using the right tools to understand your data? This new study dives into a super common statistical technique called linear regression and asks if we're really checking all the right boxes. So picture this, you are doing some research maybe in psychology, and you run this statistical analysis called linear regression. It is like a workhorse for understanding how one thing might predict another. But like any tool, it works best when certain conditions are met. These are called assumptions. Two big ones are that your data should be normally distributed, meaning it forms a bell curve, and homoscedastic, meaning the spread of your data is roughly the same everywhere. Now, what happens when these assumptions aren't met? Does it mess up your results? And how do we even know if they're not met in the first place? That is the puzzle our researchers set out to solve. The abstract tells us violations of these assumptions, especially homoscedasticity, can really mess with the validity of your findings. They noticed that software like SPSS already has tests for these issues and ways to get around them. So the common practice is to test for problems. And then, if there is a problem, switch to a more advanced method. This study wanted to see if that too. Step approach actually works, especially when assumptions like normality and homoscedasticity are violated, or when both are violated. They also looked at how well different testing methods performed and compared 4 different ways to do the regression analysis itself, the classic way, and 3 robust ways that are supposed to handle problems better. The introduction highlights that if you violate these assumptions, your statistical tests might give you the wrong answer. And here is the kicker, these assumptions are about the whole population, but we only ever have a sample of data, so we have to use our sample to guess about the population, and that guessing game itself can be tricky. If we're wrong about whether assumptions are violated, we might either use a complex method when we don't need to, or worse, use the simple method when it is actually giving us bad information. This study's goal is to help applied researchers, especially those using common software like SPSS, by examining the tools available there. So, how did they test this? They ran a big simulation study. Think of it like creating a bunch of fake datasets in a computer. They created datasets with different sample sizes, from small ones with only 25 data points to larger ones with 500. They also deliberately played with the data to break the assumptions. They created errors that were normally distributed, and errors that were symmetric but had heavier tails than normal, and errors that were both skewed and had heavy tails. They also created different patterns of variance, which is related to homoscedasticity. Some had constant variance, others had a funnel shape where the spread increased with a predictor, a butterfly where it was high at the extremes and low in the middle, and an inverse butterfly with high variance at the middle and low at the extremes. They did this for 2 main reasons. First, to see how often their tests incorrectly flagged a problem when there wasn't one. That is called the type I error rate. And second, to see how well their tests could actually detect a problem when it was there. That is called power. For understanding how well the regression methods themselves worked, they simulated data where the true coefficients were 0 to check type I errors, and where they were 0.5 to check power. They ran 5,000 of these simulations for each condition to get reliable results. Let's dive into what they found. First, about the regression methods themselves. This figure shows the type I error rates. When all assumptions were met, all 4 methods, the classic one and the 3 robust ones, did a great job, with error rates very close to the expected 5%. But things got interesting when assumptions were violated. For the coefficient linked to the predictor that caused the heteroscedasticity, the classic method often failed. In the funnel and butterfly patterns, the type I error rates were too high, meaning they wrongly found significance too often. In the inverse butterfly pattern, it was too low, meaning it missed significance too often. The robust methods, however, generally kept their type I error rates within acceptable limits even when things were messy. Now, let's look at power, or how well these methods find the real effect when there is one. Generally, when assumptions were violated, all methods had less power, heavy-tailed distributions. Both symmetric and skewed really hurt power across the board. Next, the performance of the assumption tests themselves. When they tested for normality, the Z-kurtosis test and the Shapiro-Wilk test seemed to be the most powerful at detecting deviations from normality. Interestingly, they also tended to flag deviations from homoscedasticity because heteroscedasticity often makes the residuals look less normal. When they tested specifically for homoscedasticity, things were more varied. Some tests, like White's test, did a decent job in large samples if the errors were normal, but struggled if there was non-normality too. The Bruch-Pagan test with the model specification showed better power, especially when non-normality was present. However, generally, No single test was the absolute best across all situations. This figure highlights a selection of the best assumption tests. The Z-kurtosis test and the Shapiro-Wilk test were good at detecting deviations from normality. White's test was decent at detecting heteroscedasticity, when errors were normal, but Z-kurtosis became better when non-normality was also involved. The key takeaway here is that the Z-kurtosis test seemed to be a consistent performer for detecting either normality issues, homoscedasticity issues, or a combination of both. Now, for the big question, does that two-step approach actually work? They simulated a process where they first used the Z-kurtosis test. If it found a violation, they switched to a robust regression method. Otherwise, they stuck with the classic method. For the coefficient that was not affected by heteroscedasticity, that is coefficient B2 in their study, the type I error rates were mostly okay, but for the coefficient linked to heteroscedasticity, coefficient B1 in their study, this two-step approach caused problems, especially in small samples. Type I error rates went outside the acceptable range when heteroscedasticity was present, similar to when using the classical method alone in those problematic scenarios. Looking at power for the two-step approach, it didn't really offer much of an advantage over just picking a robust method from the start. In some cases where the classical method was performing poorly, the two-step approach helped by switching to a robust method, but in other cases it made things worse by switching away from the classical method when it might have been better. So, what does all this mean? The study confirms that violating assumptions in linear regression can indeed lead to unreliable results with the classic method, especially when heteroscedasticity is tied to the predictor you are interested in. Deviations from normality alone didn't seem to cause as many problems for the classical method in their simulations, which aligns with other research. However, when you combine non-normality with heteroscedasticity, even the robust methods can struggle with type I error rates in small samples. They found that the Z-kurtosis test was a pretty good all-rounder for spotting problems with normality or homoscedasticity. However, their main conclusion about the popular two-step approach is quite stark. In small samples, it often doesn't control type I error rates well because the assumption tests themselves lack power. In large samples, it provides no real benefit, as you could have just used a robust method from the start with similar or better results. They essentially state that formally testing assumptions to decide on a method isn't always dependable or helpful. The authors can generally not recommend this typical two-step approach to inference in linear regression problems. They suggest that instead of relying heavily on assumption tests, it might be better to routinely use robust inference methods. Perhaps combining classical inference with robust standard errors like HC4 and a bootstrap method like the while bootstrap. They also emphasize the importance of visually inspecting your data, looking at scatter plots to understand the nature of any potential heteroscedasticity. This visual inspection can help you decide which inference method to trust more. For example, if you see a funnel shape, HC4 might be better. If it is an inverse butterfly, maybe the pair's bootstrap is preferable. Ultimately, understanding your data qualitatively can guide your quantitative analysis. This research is really important because it challenges a common practice. It suggests that blindly running assumption tests and then switching methods might not be the most reliable path to accurate conclusions, especially when dealing with smaller datasets. It highlights that robust methods are powerful tools that can often be used directly, and visual inspection of data is a crucial step that shouldn't be skipped. It makes you think about how we approach statistical analysis and whether we can simplify things and get better results by being more direct with robust techniques and by really looking at our data. If you found this breakdown helpful, please give this video a thumbs up, leave a comment with your thoughts. And don't forget to subscribe to RUBIN'S Mind Lab for more insights into the fascinating world of research. Thanks for watching.